Hey guys, it's Mr. Ray here with our next calculus lesson. We've reached double digits now. This is the 10th lesson with the distance learning. Hope you guys are doing well. I know this is a big change for everybody. It's kind of tough to learn math when you can't ask questions right away. Can't work with your friends directly, but hopefully you guys are finding a way to get this to work. I hope the video lessons are helping. I know a handful of you are making use of the office hours. So I urge you, if you're getting stuck on stuff, please just join the office hours anytime you can. Um, I think last week I had a grand total of 3 people over the 4 hours, so there's plenty of room, plenty of time for you guys to ask questions. Okay, so this is lesson 10. In the old unit system, this would be unit 6, called derivatives. So it's all about derivatives. Yeah, we haven't officially used that word yet in the classes. I did introduce at the beginning of uh, the calculus part about the calculus is made up of two types of mathematics. One's called the derivative and one's called the integral. So like I said, we're just doing derivatives in grade 12 calculus. If you're taking calculus in the university, you'll be introduced to integrals as well. So what's a derivative? Well, you guys have actually been doing derivatives without knowing that they were derivatives because, of course, we didn't call them that. But the best way to think of derivative, it's a function, as you can tell by the title here. Just like you have a square root function and a sine function and all sorts of different math functions, the derivative is another function. So what does the function do? Well, it gives the slope of a tangent at a point along a given function. Okay, and we've been doing this. Like I said, the last unit we were finding the slope of a tangent at a point by finding the limit of finding the slope of the tangent by taking the limit of the function between 2 points, and we had this value h that basically decreased to 0. And so when we were taking the limits, we were finding the slope of the tangent, and on top of that, that whole process is called the derivative, okay? So here's the formal definition. The derivative of function f at a point a, comma f of a is, now here's something new. So instead of saying slope of a tangent or the limit, we have this new notation here. So it looks, if you're taking the derivative of a function f, well, that becomes f. Well, it stays f, but you have this little quotation symbol, single quotation, and the way we would pronounce this is the word prime. Okay, so I would say the derivative is f prime of a, so it's still a function, like we've just said. So f prime of a is the derivative function of f of a. Okay, and how do we get that? Well, we get that by doing what we've been doing with the limit as h approaches 0 of f of a plus h minus f of a over h, which is basically, rise over run between 2 points, where those 2 points are getting closer and closer together to the point where they're the same point. Okay, and here's another way of saying it here, with the function notation with x and a being the second point. Okay, we'll talk about this a bit later. A function is said to be differentiable. That means you can take the derivative. It's differentiable at a if the derivative at a exists. So that makes sense. A function is differentiable, means a function, you can take the derivative of a function on an interval, like between two values of x, if it's differentiable at every number in the interval. Okay, and you'll see most functions are differentiable everywhere for domain, for all the domain, but there's some situations where it's not, and we're going to look at that. Okay, so again, we have this, this is basically repeating ourselves there. So this is an important thing. It kind of puts everything together. The derivative f prime of a can be interpreted as either one, the slope of the tangent at that point, or two, the instantaneous rate of change of f of x with respect to x when x is that point A. So all three of these things are the same. Instantaneous rate of change, the slope of the tangent, and the derivative are the same thing. Okay? You just use it in different context. Okay? Now, we'll get into this one here a little bit later, but there's different ways. We've already talked about this notation of the derivative, f prime of x. Sometimes, sometimes we might define a function as y equals, y equals 2 plus 5. In that case, we'd say the derivative, since it's not in function notation, we would say y prime is equal to whatever value or whatever expression. Okay, so that's the second way of notation. And that's this last one will come in towards the end. You probably think that this is pronounced dy by dx, but for some reason, I have no idea. When I was taught this in school, it's called dy dx. Okay, so I'll just dy dx. Doesn't really mean it's dying. I really don't. I think it's just, it looks like the word dy dx. Anyways, that's more for next year in university. If your prof starts saying that, you'll understand that it's, oh, that's the dy over dx. Okay. And then this thing, we kind of actually learned this. Hopefully you learned this during one of your assignment questions. I think it was a couple of weeks ago, about the normal of the tangent. So the normal to the graph of a function at point P is a line that's perpendicular to the tangent line. Okay, so this brings a little bit of vectors in, and also that kind of thinking question I had a couple of weeks ago, where you had to find the slope of the normals. Okay, and I think a lot of you did a great job on that. So that should make sense already. Okay, so now we've got a couple of examples to go through. So this one is find the derivative of a function at a specific point, meaning I don't want the derivative of the function. I want the derivative of a function, say x equals 5. So we'll go through that for this. And the next question is more general. What's the derivative of the function? And then we can use that to find the derivative of the function at many points. Okay, this will be a specific point. In this case, it's x equals -3. And the function we're looking at is f of x equals squared. Okay, so we'll start using our new notation. So we're taking the derivative of the function f. So that means we're going to look at f prime. Now, instead of saying x in this case, which we would normally do if we're taking the derivative of the whole function, we're trying to find the derivative at x equals -3. So in this case, we would put f prime at -3. And this is where we use the limit like we've always used it. That's equal to the limit as h approaches 0. And so normally it'd be f of x plus h, but this time we're looking at x being -3. So it's f of -3 plus h minus f of -3 all over h. Okay, now here's where we'll keep that limit going on the left side there. Here's where we actually use the x squared part. So each of these goes into, gets squared. So on the top it's -3 plus h squared minus -3 squared over h. Limit as h approaches 0. Okay, so when we break this, when we square this, we're going to get 9 minus 6h plus h squared, and then that's going to be 9, so it's -9, and you can see the 9's cancel. Well, let's do that now. This is all over h still, and now you can see you know, as normally happens, you can now actually cancel the h's because that's all you have on the bottom, and each term on the top has an h. So limit as h approaches 0 of -6 plus h. Okay, and at this point, this is the first time we can actually plug in h equals 0 because it's approaching 0. Before we couldn't because of the divide by 0 issue, as per normal. So now this is going to be the final answer. I mean, you've got f prime of -3 going all the way down here. Just to repeat it up here, f prime at -3 is equal to, and now when we plug a 0 for the h, we get -6. So that's what we're looking for. The derivative of f of x at x equals -3 is -6. So let's just say that. You won't have to do this all the time, but this is just the learning part. The derivative of f of x equals x squared at x equals -3 is -6. Okay, so that should seem very familiar based on what we've done in the last unit. The only new thing is we're calling it a derivative, and we've got this new notation. Instead of calling it the slope of the tangent or the instantaneous rate of change, we're calling it the derivative f prime, which is the derivative of f at the value -3. Okay, so the next example, similar type question, except this time we're not looking at a specific point, we're looking at what we call an arbitrary point, or which really means any point. So instead of plugging in -3 for x, we would just keep the x, and you've done this before. This would be called the general slope formula, the general tangent formula. So in this case, same function, f of x equals x squared. This time it's just general formula for x. Okay, and this is what we'll be doing in the future. We get a general derivative function for x squared, and then we can just use that for any value of x. We don't have to keep doing that whole process we just did in example 1 over and over. Okay, so this time f prime of x, because we're doing the general formula for any point x, and this will be the same, except instead of putting -3, we've got f of, should be, that limit's right out front. So the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, and now like we did last time, we plug in the input that's for the function f into the value here. So x gets replaced with x plus h. So x plus h squared minus x squared over h. And then we're going to square that, so we get x squared plus 2xh plus h squared minus x squared over h. So it's a little familiar to the last question, except, you know, we didn't have 2xh here. I think we had 6xh, and we had, you know, -3 squared 9 here and 9 here. But regardless, they'll still cancel out. And you can see again the same thing happens. We can actually cancel at h because the top numerator terms all have h's. So this is going to be 2x plus h. And at this point, you can actually plug in the h being 0. So all you're left with is 2x. So if you bring this up to the top, we get f prime of x is equal to 2x. Okay, so this is actually a lot more valuable than just doing it for f prime at -3, because now we could do it for any point we want. So for example, you know, I could use this. Let's try -3 again. So when I plug -3 in there, I get -6. So this is the derivative function. I just input the value of x where I want that derivative, and it's -6, which is the same thing we got in example 1. But you can keep going. What's the derivative at x equals 1? It's going to be 2 times 1, 2. What's the derivative at 0? It's going to be 0. Okay. Now the cool thing about this is, what are we actually doing here? Well, remember the derivative is the slope of the tangent at that point, or the instantaneous rate of change. So just using that function, this derivative function, we can say, oh, the slope of the tangent of the function f of x equals x squared at the point 0, x equals 0, is 0, which means it's a flat line, and that looks right. Or the instantaneous rate of change at x equals 0 is also 0, okay, because you can tell later on we'll realize, oh, that's where the vertex is for the f of x equals x squared. That's where the function changes direction, so the slope of the tangent is 0. Okay, so these are all slopes of tangents at the various values of x. Okay, so here's the definition again. We've already covered that. I just kind of threw it in there. Let's do the example 3. So this time, the function we're looking at, f of t, it's probably time-based maybe, f of t is the square root of t. So we want the derivative function f prime of t. Okay, and obviously t has to be greater than or equal to 0 because the domain for that function f has to be, can't be negative because you can't take the square root of a negative number, so that's why that restriction is given. So let's try this out. F prime of t is equal to the limit as h approaches 0 of f. Now let's keep our variable straight. This time we're using x, right? So I know sometimes it's easy to keep putting x there, but just look back over here and you'll see what the variable that we're using is. Okay, so this is pretty standard now. So now we actually go back and say, well, what's function f do? It takes the square root, so that this is where we actually change it from function notation to the mathematics of that function. So this is going to be the square root of t plus h minus the square root of t all over h. Okay, now this does not cancel things on its own like the last two, but if you remember, this is where we would use the rationalizing the numerator. So we multiply both sides by the conjugate of the numerator. And you know that's going to actually help us get rid of the h. Even though it sounds like we're just doing it for the numerator, we're actually doing that to get rid of the h on the bottom. So this is going to be, remember the conjugate, think of this as your first term, this is your second term. So since we have a minus sign between, the conjugate would be the exact same but with a plus sign. So same thing, top and bottom. Okay. Now on the top, let's do the shortcut, right? Because you know the outside and the inside multiplications are just going to cancel each other out because this is like kind of a difference of squares. So what we're going to have is this squared. So it basically is the square root squared, just gets rid of the square root sign, and that's going to be subtracting whatever this is squared. So that thing squared is just t. Okay, so that's why we do the conjugate, is because it simplifies it down to here. Now on the bottom, we're just going to leave it. We're not going to expand it because you know we need to use that h. We're going to cancel that h. So it's just more work if you expand. Okay, so you can easily see the t minus t and plus t canceled, and you're left with the h by itself on the top. That cancels with the h on the bottom, leaves a 1. It's important to leave a 1 because you're dividing by h, not subtracting it. Okay, so what do we have left over? We have a 1 on the top and t plus h, t plus h square root plus square root of t all on the bottom. Okay, so at this point you can actually, for the first time, you can actually plug in h equals 0 because when you plug it in here you just get the square root of t plus the square root of t, and squeeze one more row in here. What do we got here? Oh, now we're actually going to sub in h equals 0. So we don't need the limit anymore. So we've got a 1 on the top. We've got a square root of t plus the square root of t on the bottom. Okay, so let's go back up here. So we can simplify this. If you think of square root of t as its own variable, we've got 2 of these things now. So this is going to be f prime of t is equal to 1 over 2 root t. And that's what we're looking for. And we still have to be careful because that restriction on t that we had for the function f also applies to the derivative. So I should include for t greater than or equal to 0. Okay, so that's the derivative function of the square root function. Okay, and if we want to find the derivative of any value of t, we could just at this point plug it in. For example, f prime of 9 would be, plug it in 9 here, that's going to be 3, it'd be 1/6. Okay, and you can see, we'd still have a problem. The reason why that restriction holds is because it would still be a problem for the derivative. You try to plug in a negative number here, it's gonna give us some grief because it's not going to work. Okay, so the restriction on the function carries through to the derivative function. Okay. So next example 4. So we start off with that the last key concept about the normal being perpendicular to the tangent. So we're going to actually use that here, using the derivative to determine the equation of a tangent. Oh, maybe we're not. Yes, we are. Okay. Determine an equation of the tangent to the graph f of x equals 1 over x at the point where x equals 2. Then find the equation of the normal perpendicular to the tangent at the same point. Okay, so we're being specific this time. We're not. We're looking at the point on the. If we plug in x equals 2 into the function, into f of x, f of 2 is 1/2. So the point where we're looking to find the slope of the tangent and the slope of the normal as well is at 2 1/2. So it's sometimes they'll give you the point at the x and y value, and sometimes they'll just give you the x. So it's easy, just plug that back into f to get the y coordinate. Okay, because we're going to need that later. All right, so let's do the general formula here. We don't have to, but I'm going to because it's could be useful. So again, this is the limit of, as h approaches 0, of f of x plus h minus f of x over h. Okay, so this function now is 1 over x. So this is going to be 1 over x plus h minus 1 over x all over h. So this is a little tricky on the top here because we want to combine them into one term, but the denominators are quite different. So we're actually going to come up with, a common denominator of x times x plus h, just multiplying the two denominators together. And in order to come up with the new numerators, for example, this term we're multiplying by x over x. So that would be x on the top for there, and then we subtract from there. The top here will be x plus h. You have to be careful on this because you have to put brackets because it's being subtracted. If it was being added here, no big deal, but big deal in this case. Okay, so, and this is all over h. So you can see on the top, we've got x minus x, and then this h is also minus. So we have x minus h. The two x's cancel, and all we have left is a minus h. Forgot this. Forgot the denominator there. So it's a minus h over x. Let me do this again. Give some more room. So minus h over x times x plus h all over h. Okay, and that can look a little complicated, so if we turn it into a fraction times a fraction, so there's the numerator, and if we're dividing by h, that's the same thing as multiplying by 1 over h. So this usually makes it a little more easier to understand. So that's canceling with that. You have a negative 1 on the top. So this is going to be the limit as h approaches 0 of, now I've got, at this point now I've got a negative 1 over x squared plus xh. Okay, and you can see at this point I can actually sub in a 0 for h, and this turns to 0, the xh, and we're just left with 1 over x squared. So f prime of x is equal to negative 1 over x squared. Okay, so we want the slope of the tangent. Slope of tangent at x equals 2. This is equal to f prime of 2, because slope of tangent is the derivative. So we just plug in 2 into this derivative function, and it becomes negative 1 over 4, because it's negative 1 over 2 squared, which is negative a quarter. So that's the slope of the tangent. So now what's it asking us again? It's asking the equation of the normal. Okay, so I don't need the equation of the tangent. What I do need is the normal, so the slope of the normal at x equals 2, well, that's just the negative reciprocal. Let's remember the perpendicular slopes are negative reciprocals, so that this will be 4. So slope of the normal at x equals 2 is 4, so we can start making the equation of that normal, because now we know it's y equals 4x plus b. Maybe I'll just put normal out here. Equation of the normal, 4x plus b. So all we need now is a slope that's on that normal, and a point that's on the normal. And we do have one, that point P. That's the point where the tangent is, and also where the normal intersects with the tangent. So we can actually plug in this point. I'll just bring that down here. So that's going to be 1/2 is equal to 4 times 2 plus b. So this works out. So that's 1/2 is equal to 8 plus b. So b is equal to -8 plus 1/2. So that's going to be -7.5 or -15/2. And now we just use our original equation. Y equals 4x plus b, so b is -7.5. So that is the slope, sorry, that's the equation of the normal. Okay, so you can see how we can extend our knowledge of what derivatives are and, you know, find equations of lines and tangents and normals. Okay, so this last part here, we're going to be looking at existence of derivatives. I said we'd come back to this later, and we are now. So a function f is said to be differentiable at a if f prime of a exists. So basically, if you could take the derivative exists. Okay, at points where f is not differentiable, meaning you can't find the derivative, we say that the derivative does not exist. And there's 3 common ways for derivative to not exist. So these are the conditions. So these are all at some arbitrary point a. So this is kind of the new situation we didn't see with previous examples of limits and continuity. So at this point a, you know, it kind of comes down. It's this definitely looks like a piecewise function, but it basically changes direction. But not only change direction, it it's not a smooth transition at all. Okay, so we call this thing a cusp. It's almost like a pointy part where it changes like a little mountaintop or a valley where it's not a smooth transition. The next example we look at, you'll see, you know, why isn't this differentiable? So for now, this is a new thing called a cusp. Okay, now at a vertical tangent, so you basically got a curve coming up. So this is almost like y equal x cubed on its side. You can see here that it changes direction. At this point here, you think about what a derivative is, what we just learned. It's the slope of the tangent. So, you know, the slope of the tangent here at this line, well, a vertical line you can't take, you can't find the slope of the tangent. It's, you know, it doesn't exist. And because of that, if the tangent is a vertical line, that means that by association that the derivative does not exist. So this would be called the vertical tangent. So derivative doesn't exist at a point where you have a vertical tangent. And this is, you've seen this before when we did continuity and limits. Basically, you have a gap here, like a jump, we called it for continuity. Where you have anything that is not continuous, meaning it's discontinuous, you don't have you can't take the derivative where it's discontinuous. Okay. Notice on both of these, you know, if you're looking at continuity for these look continuous, right? Because you're not picking up your pencil, but because it's a vertical tangent, the derivative doesn't exist. So what that kind of means is just because it's continuous at a point doesn't mean the derivative exists, okay? But if it's discontinuous at a point, you know the derivative doesn't exist, okay? But you can't go the other way, because if it's one of these situations, like in this case here, you'd also say, well, the limit exists, it's going to that point there. So the limit exists at point A, it's continuous at point A, but because it's a cusp, the derivative doesn't exist. Okay. Let's look at an example where you might see why that's true for that first situation. So last example, Just whether the absolute value function f of x is the absolute value of x is differentiable for all values of x. So if we do a quick little sketch of that, absolute value function, that's where it strips off the negative sign. And in a way, it's kind of like a piecewise function here because, at 0, at x being 0 and greater than 0, it's basically, you could say that this is y equals x. But on the other side here, it's y equals negative x. Okay, now, if we're looking at now we haven't done this before, if we looked at the derivative on the right side, as we're coming down towards 0, so I should put a negative sign here. So we're going to do like almost like a one-sided derivative here, just like we did one-sided limits. So as we're coming from the negative side, we're going to do that. Also coming from the positive side of 0, what is the derivative as we're approaching from both sides? So in this case, so let's do this one first. As you're coming from the negative side towards 0, you can see that the slope, or the derivative, slope of the tangent, is going to be -1. So as we're coming down towards that point 0, you could say that the derivative is approaching, well, for every value along there, the derivative is -1. On the other side, on the right side where x is positive, the derivative is +1. Okay, obviously these two values don't match. So we're kind of doing almost like the same thing we did with limits, but it's not the same as limits because you would say the limit exists, but in this case the derivative does not exist because the derivatives aren't approaching the same from both sides. So in this case, the derivative does not exist at x equals 0. Now, that doesn't mean the derivative does not exist at any other points. In fact, this is the only point of f where the derivative does not exist. Every other value of x, the derivative does not exist. Okay, so it's a very unique point. The only value of x where the derivative does not exist, but it does exist everywhere else. Okay. All right, so that introduces the term derivative. It's a function, which is basically the same thing we've been doing with limits, slope of the tangent, and the instantaneous rate of change, exactly the same thing as taking the derivative. Okay, now this whole process, if I just go back, previous page, this whole process of finding the derivative using, the limits, okay, we won't be doing that anymore. Okay, and you'll be happy to hear that. This is to show you where it comes from first principles. That's the term. When you have an assignment this week, I will ask 1 or 2 questions where I ask you to find the derivative using first principles. Okay, and that means you have to use this technique with the limit. Now, other than those 1 or 2 questions, from now on, you'll start learning shortcuts to knowing what the derivative of different functions are, and you'll be able to use those. So that's the good news. But you still have to know how to do this on this next assignment. Beyond then, for any future assignments, you won't have to know this technique, but you will have to know it if and when we do a summative assessment at the end. There'll probably be one question where you have to do that. Okay, so hopefully this makes sense. We're going to try to do 3 lessons again. It seems to be working out well. 3 lessons this week, so 10, 11, 12. Same thing with the assignments. I'll post at 3 p.m. Friday, due Sunday at midnight, and bonus 5% if it's handed in by Friday at 8 p.m. Okay. Don't forget about the office hours. If you need some extra help, please join in. Okay, it's not a detention, it's just me helping you out. Okay, so have a great day, and I'll have the next lesson for you on Wednesday morning. All right, thanks guys.